Very good morning, students.
Good morning,
Good
sir.
morning, sir.
Morning, all of you. So let us start with the discussion without wasting any time. So last class we have been discussing about the elimination reaction, right? E1 elimination, A2 elimination. Yes. So E2 elimination we have discussed. E2 elimination is bimolecular elimination reaction. That depends upon concentration of substrate as well as concentration of the base. And if you try to think about the transient state in A2 elimination, the transient state in A2 elimination looks like a alkene system. So based on the stability of alkene only, you have to compare the rates of E2 elimination. So rate of E2 elimination is higher for 3 degree or tertiary alkyl halide, then secondary, then primary, because tertiary alkyl halide will form more substitute alkene, which will have more number of hyperconjugated structures. After that, E2 elimination will be anti-elimination. That means the base will try to pick up the proton, which is exactly opposite to that of leaving group. And also, E2 elimination will form sets of product as a major product whenever there are two different beta carbons available. Whenever there are two different beta carbons available. And if you think of the major product formation, there are some set of conditions under which Hoffman's product is also major. What are those set of conditions? In the case of bulky base, in the presence of poor leaving groups, in the case of extended conjugation, we'll discuss one by one now. So bulky base is simplest case, okay? In the presence of bulky base, like tertiary butoxide, CH3, C, CH3, CH3O minus. Now we are trying to take an alkene, CH3, we are trying to take an alkyl halide and generate an alkene, CH3, CHCl, CH2, CH3, and I'm treating this with CH3, CH3, CH3O minus. Generally what happens, base has to pick up the proton. So we have how many protons available? Two types of protons available. So what are these? CH2H and CHH. The base cannot go and pick up this proton. It is not possible because of steric repulsions. Rather, O minus picks up this proton. This is feasible. CH electron density comes into carbon chlorine bond leaves. So we'll form CH2 double bond CH, CH2 CH3. Along with that, you can also write the other product CH3 CH double bond CH CH3, where first one is going to be the major, second one will be minor, which is nothing but your Hoffman's product. Everyone got this or not? Yes or no, students?
Sir, base can also pick up the hydrogen in which chlorine is directly attached, right?
Yesterday I have asked the same thing, Faizan. Why?
Yes, sir. I'm having doubt in that also. Why would
Steric
due to state
repulsions.
propulsion?
Steric
Yes.
repulsions. Okay. Base, if tries to pick up the proton from the carbon to which halogen is directly connected, steric repulsions are dominant. That is why from the beta carbon only the hydrogen has been picked up. Okay.
Okay, sir.
Right. So we'll be getting Hoffman's product CH2 double bond CH, CH2 CH3. So this will be your respect to major product, and the other is going to be the minor product. So in the case of bulky base, whenever the base is bulky, Hoffman's product is obtained as major, where you will be having less substituted product, because the bulky base cannot experience more steric repulsions if it tries to pick up the substituted proton. Like the most substituted alkene, if you want to get, then you will be getting shades of alkene. Shades of alkene is unstable because of the same reason. Second case, extended conjugation you can think of. In the case of extended conjugation, like we have this system, treat with alcoholic OH. Alcoholic OH has to pick up the proton from the beta carbon. This is the alpha carbon to which bromine is connected. The carbon next to alpha carbon is beta carbon. So this was your beta. This is also your beta. In this beta carbon we have hydrogen. In this beta carbon also we have hydrogen. You can say alpha, beta, gamma. Yes or no? So beta carbon possesses the hydrogen, the alcoholic OH picks up the proton, and it can form two types of products. What are two different types of products you can expect? So you can expect a product like this. You can also expect product in the other fashion. Yes or no? So this is a more substituted product. This is nothing but Saitzef. This is nothing but Hoffman's, which is stable. Which is major? Like this on the gamma carbon, since we have a carbon-carbon double bond, this carbon-carbon double bond is now in conjugation with the CC double bond, which is formed new or not. So due to resonance, it is stabilized. Resonance is stabilized. That is why it is major. Although we have more substitution, look at the look at the number of hyperconjugate structure. The C double bond C is connected with two methyls. Each methyl has 3 hydrogens. So we have 6 alpha hydrogens. Here also we have alpha, 2 more hydrogens, 8 alpha hydrogens are there. So if you go with the number of alpha hydrogens and looking at number of hyperconjugated structure, you should write Saitzef. But in reality, resonance is more given the highest priority. So whenever you have extended conjugation, conjugation is extended or not? Whenever you have extended conjugation, you will be looking at the Hoffman's product as the major product, and this is how you have to write the scenario. Is that clear, students?
Yes, sir.
Yes.
Simple. Yes, right. Simple case. Then in the third case, we are explaining about in the case of poor leaving group. In the case of poor leaving group, like fluorine is a poor leaving group. Why? Like fluorine, Nr3 plus, Sr2 plus, these are the poor leaving groups. Why? Because the carbon fluorine bond that cannot be broken easily because of greater overlapping. So I have taken this particular alkyl halide CH3, CHF, CH2, CH3, and I am treating this with a alcoholic OH only, not a bulky base. If I take bulky base, then you can say because of bulky base we are getting Hoffman's. But I am taking alcoholic OH, which is not a bulky base. Alcoholic OH has to try to pick up the proton. Two cases are possible. But now what is going to happen is, look at the transition state, and I am explaining the transition state for the most stable transition state. CH3, CHF, right? CH3 can write as CH2H. The alcoholic KOH tries to pick up this particular proton. So you'll get a CH2, H, and OH. And you have CHF, and you have CH2, CH3. So this is nothing but your TS. TS means transient states. Understand the difference carefully. Earlier, what we have written, students, whenever we have written the transient state in the case of good leaving group, like carbon chlorine bond, if I there, then how I have written? The CH electron density is supposed to be moving in this fashion, so we get a pi bond. This carbon fluorine bond is supposed to leave, so we have here also I have kept the dotted lines. But now I am keeping a dotted lines between the carbon-carbon single bond, that is pi bond I am not writing, and CF bond also I am not breaking. They are represented with a solid lines only. Why? This CF bond is a stronger bond that cannot be leaved easily. If that cannot be leaved easily, this pi bond is also not formed so easily. So OH minus is a base which is picking up the proton, that's fine, that is happening. CH electron density is not now directly given as pi electron density, rather the CH electron density is given to the carbon. So how the transient state looks like? The transient state in the case of poor leaving groups looks like a carbon ion, not your respective alkene. Understand this point. Transition states in the case of, I have to talk of only transient states because E2 reaction happens in single step. Although it is single step, there is always a transient state. Transient state in the case of poor leaving group represents a carbon ion, and not an alkene, So this is how your transient state is looking like: CH2 minus, CHF, CH2, CH3. Or you can also have other transient state: CH3, CHF, CH minus, CH3. Among these two, which is more stable?
First one.
First one, because carbon ion stabilities we have to compare. It is a primary carbon ion, it is secondary carbon ion. So more stable is the first one. Yes or no? Less stable. So primary carbon ion is more stable. That is why this transient state is obtained. Now this negative charge comes into, then the CF bond leaves. Understand this point carefully. Sir, again you are writing the same alkene. No, you can ask a question. Yes, we are writing the alkene as a product only, but the transient state is not looking like alkene. The transient state is looking like carbon ion. Once the negative charge is developed on this carbon greatly, then the negative charge comes into, then the CF bond is pushed away. It is not pushed directly by the CH electron density and CF bond. The negative charge is developed on the carbon for longer time, and then the negative charge comes into, CF bond is broken. So you will get CH2 double bond CH, single bond CH2 CH3, which is nothing but your major. Hoffman's product is major. Everyone got this or not?
Yes, sir.
Okay. Transient state in the case of E2 elimination looks like alkene. Transient state in the case of E2 elimination, where you have a poor leaving group, looks like carbanion system. And if it is carbanion, you have to go with the more stable carbanion. We cannot say Hoffman's or Saitzef. That is the next other scenario. We have to go with the stabilities of the transient state. Alkene is a transient state. You just proceed with that particular alkene, which will be having more number of substitution. If a more carbanion is a transient state, you just proceed with that particular compound where you will be getting most stable carbon ion. Yes or no? Or most stable transient state. Understood this point? Here also you get the least substituted alkene, which is nothing but your Hoffman's alkene. Example, try to solve this question. CH3, or you can write pH, CH2, CHF, CH3, alcoholic KOH, forms pH, CH2, CH double bond CH2, Hoffman's, and you can write Saitzef's. This is compound A, this is compound B, which is major and which is minor. pH, CH2, CHF, CH3, and if you try to proceed with the Hoffman's product, Saitzef product logic, which is to be major and which is minor? Because CF is a poor leaving group or not? Yes or no?
Yes, sir. Yes.
So poor leaving group means you will be getting Hoffman's product as a major. So what should happen here? Among A and B, which should be major and which should be minor?
Sir, B will be major.
Why, Suman?
Sir, we got conjugation is there on a carbanion.
So then the statement is wrong, right? So in the case of poor leaving group, always Hoffman's is going to be major. That statement is wrong or right?
According to question, it's wrong.
It will be wrong. Okay, that statement, whatever you are saying. Okay, here what are the statement? In the case of poor leaving group, you cannot say always Hoffman's product is obtained. In the case of poor leaving group, the major product is always, the major product will be formed. The major product will be formed where the more stable, carbon ion is obtained. Because the transient state stability you have to look at, it's not like Saitzef or Hoffman. You have to proceed with the transient state stability. So you have to go with the transient state. So if you have pH, CH2, CHF, CH3, this is alpha carbon, this is beta, and this is also beta. So OH minus, if it tries to pick up this proton, OH minus, if it tries to pick up this proton, you get a CH electron is given to carbon. You have pH. pH is nothing but phenyl group having this type of structure. And you have CH with a negative charge on this particular carbon. You have CHF and CH3. This negative charge on the carbon is actually in resonance with the pi electron density or not. Okay. This is a benzylic carbon ion which is resonance stabilized. Benzylic carbon ion type and is resonance stabilized So what will happen now? Since it is a benzylic carbon and is resonance stabilized, you have this particular carbon ion formed. Okay, not the other carbon ion. So negative charge present here. That negative charge comes into, then the CF bond is going to broken. You will get this type of system, CH double bond CH, CH3, and it is the Saitzef only. It is not Hoffman. So it is not about Saitzef or Hoffman product. It is all about the stability of carbon ion, which is the transition state. Is that clear or not?
Yes, sir.
Okay, it is major. And let us solve some critical examples. Okay. So like critical examples in the case, a slightly difficult examples. So I'll be giving different types of compounds to you now and try to ask the question. You think of such questions like you may not be experiencing directly such type of questions in the exam, but any part of that question can be in the exam. Like one part of the question can be in the exam. Solve this question. CH3C, PHH, ClCH3, pH. You are treating this with C2H5O minus. You get a compound A. You get a compound A. And you treat the other molecule CH3, CPHH. Like these are nothing but Fischer projections. You all know, right? We have solved different examples as well. CH3, PHH, ClPH, CH3, treating with NaNH2, Na plus NH2 minus, we get B. Among A and B, which boils first? Among A and B, which boils first? Everyone got the question or not? First, A and B are the same compounds. Check out carefully. CH3, CHPH, CCH3, Cl and pH, CPH, CH, CH3. So the compounds, whatever they have given to you, the substrates, whatever they have given to you are like isomers only. Yes or no? The substrates, whatever they have given to you are isomers only. You have to find out what are A and B. I am treating a respective compound with C2H5O minus. If you look at the respective compound, it is like an alkyl halide or alkyl halide or not? Yes or no? The respective substrates, you look carefully, students, they are simply your alkyl halides. Alkyl halides treated with a respective alkoxides. Alkoxides and NaNH2, they are very strong bases. Alkyl halide treated with strong bases. What type of reaction should be coming into your mind? What type of reaction should be coming into mind? You have to always think of. What type of reaction? Alkyl halides, strong base. Answer this. Right or wrong, not an issue.
B2.
E2 elimination. Yes or no? E2 elimination you have to think of. The solution goes like this. So I am talking with the first compound CH3, CPHH, CCH, Cl, CH3, But E2 elimination, what is the stereochemistry of E2 elimination? E2 elimination will always proceed through. E2 elimination is always happening in the anti-direction. That is what we know. E2 elimination will be always happening in the anti-direction. That means the hydrogen which is picked up by the base and the leaving group like halogen, halide ion, they should be exactly opposite to each other. Now try to, this Fischer projection is a two-dimensional representation of a three-dimensional molecule. this is this Fisher projection, whatever I have mentioned here, that is a 2D representation of a 3D molecule. But we have to write the 3D molecule, because then only we'll find out whether this is a alpha carbon. I can say this is alpha carbon because it is a carbon to which halogen is connected. It is the beta carbon. On the beta carbon you have hydrogen. I cannot directly say hydrogen and chlorine are opposite. I cannot directly say hydrogen and chlorine are opposite because it is not the exact representation. It is a 2D representation of a 3D molecule. It is a Fisher projection. So I have to understand how the hydrogen and chlorine are present in space. So for that, you better draw the Newman projection. So I am going to draw the Newman projection. Can I say this CH3 and this pH, they have same, they are present on the same sides? Yes or no? This CH3, the vertical groups, CH3 and pH, they have same spatial arrangements. The pH and Cl, H and CH3, they will also have same spatial arrangements. Same, and CH3 and pH, they are going to be same. Now I am trying to write the front carbon as well as the back carbon. The front carbon is represented by a dot. In the front carbon, you have, this is my front carbon. Let us say I am looking at this molecule in this fashion. Front carbon, to the front carbon, CH3 is connected to the top. pH is on the right side, H is on the left side. On the back carbon, here I am standing, students. Here I am standing and I am looking at the molecule to this beta and alpha carbon. To the front carbon, CH3 is top, pH is on the right side, H is on the left side. To the back carbon, what is my scenario? To the back carbon, what is my scenario? pH is on which side? pH and CH3. This pH and this CH3, they should have same. So pH will be somewhere here. This Cl and this pH, they should be also having same orientation. And this hydrogen and this CH3, hydrogen and this CH3, here we should have CH3. Everyone understood how to draw the Newman projection or not? Yes or no?
Yes.
Yes, sir.
From the respect to Fisher projection, I have converted into respect to Newman projection so that to understand where the groups are actually present in space. Now, what is the only condition we have is anti-elimination should occur. Anti-elimination should occur means, okay, E2 elimination proceeds. E2 elimination is anti or anti. So what happens? The leaving group chloride, that is chlorine, and the hydrogen, they should be exactly opposite to each other. That means they should be at an angle of 180 degree. So what is the angle between hydrogen and chlorine now? Try to figure out. Hydrogen and chlorine, they are at an angle of how much? Dihedral angle. Can I say dihedral angle here is 120 degrees or not?
Yes, sir.
Yes or no? Dihedral angle, because the total 360 degrees is divided into three parts. 360 by 3 is 120. So the hydrogen and chlorine, they are at an angle of 120 degree. So you have to rotate the carbon, either the front carbon or back carbon, in such a way such that the dihedral angle is now going to be 180 degrees, such that hydrogen and chlorine will be exactly opposite. So I have to rotate. I am rotating back carbon in which direction and by which degree. This is the back carbon. The back carbon I am rotating. I have to rotate in the clockwise direction or anti-clockwise direction.
Anti-clockwise direction.
Rotate back carbon by how many degree? By
60
degree
degrees.
in anti-clockwise direction. So what happens in that case? The front carbon is a dot which has methyl above, pH and H in this fashion, and you have chlorine now will be here. Anti-clockwise direction I'm rotating, right? Methyl will be here and pH will be here. Anti-clockwise direction rotation I have done. Now the C2 hydrogen and chlorine, they are exactly opposite or not? Now the C2H5O minus come into picture. The C2H5O minus, which was a base, that will try to pick up this proton. The CH electron density is given to the carbon-carbon single bond, and down the carbon-carbon single bond is converted to double bond. So carbon-carbon double single bond is now converted to double bond. You have what? You have methyl here. You have methyl here. On the front carbon, you have methyl and pH. On the back carbon, you have methyl here and pH, right? And this pH. So what type of configuration is this? So carbon-carbon double bond. So I can write this molecule as, this molecule can I write in this fashion? So E2 elimination is anti. Try to write this molecule. So I can write carbon carbon double bond. On the front carbon you have methyl, on the back carbon you have phenyl. They are on the same side. Front carbon methyl, this is front carbon. Back carbon phenyl, they are on the same side. Front carbon phenyl and back carbon methyl, they are on the same side. So what type of compound you are getting here? Cis or trans?
Trans.
Trans product. Okay, the trans can be obtained, cis can be obtained. That's not an issue. That depends upon the orientation. The only condition in E2 elimination is you have to produce the anti-elimination. You have to do anti-elimination only. So this is the first compound which you have obtained. Can you do in the same way for the second compound? Second compound is given to you in this fashion. CH3. What is the second molecule given to you? CH3. What is stereochemistry? PHH. PHH. ClPHCH3. ClPHCH3. Now I am writing that in the Fischer projection. Front carbon, back carbon. Front carbon, methyl is connected. This methyl to the front carbon, hydrogen and pH are connected. Where is hydrogen? Hydrogen is on the left side, pH is on the right side. This hydrogen and this pH I have substituted. Back carbon, I am looking at this carbon carbon bond. For me, back carbon, this methyl will have same stereo position as that of avomethyl because they are on the vertical. This pH and H should have same. So pH should be somewhere here. This chlorine should also be having same. This is nothing but your Newman projection for the same Fischer projection. So you have to convert the chlorine and hydrogen. They are at an angle of 120 degree now. So I have to make them 180 degree. So I have to rotate back carbon. I am rotating, keeping the front carbon constant. Rotate back carbon by how many degree and in which direction?
60 degree clockwise.
60 degree in clockwise direction. So if I do that rotation, what will happen? What will happen? I have CH3 connected above, pH here and H here. And now 60 degree clockwise, so pH will be somewhere here. And you have chlorine here. And you have methyl here. Now chlorine and hydrogen, they are having exactly 180 degree. So I can do anti-elimination. Anti-elimination is going to happen. NH2 minus is the base. So that NH2 minus picks up this proton. The CH electron density comes into. And loss of ammonia will happen. So we'll have what? We'll have carbon carbon double bond now. Front carbon is connected with a methyl and also pH. Back carbon is connected with methyl. Where is methyl? In this direction and also pH. So can I write the same as carbon carbon double bond in the front carbon and back carbon? Front carbon methyl and back carbon methyl, they are on the same side. Front carbon phenyl and back carbon phenyl are on the same side. So what type of compound is your B? This is your compound A. Compound B is cis. So among A and B, which will be having? Among cis and trans. Therefore, A and B are cis trans isomers. Cis trans isomers. And which will have higher boiling point?
Cis.
And
Cis.
cis will have higher boiling point as mu net is not equal to 0. Yes or no? So which boils first? Among A and B, which will be boiling first? Trans will be boiling first. So A, trans is nothing but A. A will be boiling first. Understood now? It's a very interesting example where you can understand that in the E2 elimination, you can get cis and trans both. It is not like trans is the major. You cannot directly say that. E2 elimination condition is only anti-elimination. It is not about cis and trans. You can have 100% cis, no trans. That depends upon stereochemistry. Stereochemistry plays an important role. Right? Try to solve one more compound. One more example. So A is the simplest optically active alkene. A is the simplest optically active alkene. A treated with a simplest optically active alkene that has been treated with a simplest optically active alkene that has been treated with H2 in the presence of palladium forms B. B treated with a Cl2 in the presence of H mu, you get a mixture of monochlorinated products. Find the total number of isomers in the mixture of monochlorinated products, including stereoisomers. Try to solve this, all of you. A is the simplest optically active alkene treated with a H2 in the presence of palladium, got B. B treated with Cl2 in the presence of H mu, produced mixture of monochlorinated products. We have to find out the total number of isomers in the mixture of monochlorinated products. We'll solve this example and then proceed with even elimination. What will happen in this case, students? So what is compound A? Can anyone say? A is the simplest optically active alkene. It is a simple alkene, they said. That means no other functional groups are there. So optically active, simplest optically active means that compound should be having only one chiral carbon. Can I say like that or not? Only one chiral
Yes.
carbon should be there. Carbon should be only one chiral carbon should be there. And to call that particular carbon as a chiral carbon, all the four groups should be different groups. What are the four different groups which you can have? One can be hydrogen, because simplest they are talking about. Other can be methyl. Other can be ethyl. And since it has to be alkene, I have to consider other has CH double bond CH2. Can I say this is my A or not? Understand this point carefully, students. I can call this as my compound A. Why? Because it is an alkene, so I should have CH double bond CH. So it has to be present as substituent, because none of these carbons can be chiral. Because to call it as a chiral carbon, that should be sp3 hybridized. You cannot have sp3 hybridized carbon in CH double bond CH2. So it is not going to be a respective alkene which you are thinking about. Yes or no? So it has CH double bond CH2 has to be taken as substituent. CH double bond CH2 has to be connected to a carbon, where that carbon has to be connected to hydrogen, methyl, and C2H5. Now treat this with a H2 in the presence of palladium. What will happen now? CH3, CH, C2H5, CH double bond CH2. If you treat with H2 in the presence of palladium, you will get CH3, CH, CH2, CH3, and CH2, CH3. Yes or no?
Yes, sir.
It is nothing but CH3, CH2, CH, CH3, CH2, CH3. I can write this compound in this fashion. This is nothing but your B. So compound A is the simplest optically active alkene treated with H2 in the presence of palladium. I got a compound B. So hydration I have done. Hydrogenation I have done. Hydration means addition of water. Hydrogenation means addition of H2. Upon hydrogenation, I got B. Now B treated with the Cl2 in the presence of H mu. What type of reaction is that? Compound B treated with Cl2 in the presence of H mu. It comes under which category? Compound B, free radical what? Free radical elimination or free radical substitution or addition?
Addition.
Addition, Fatima. In the case of addition, will happen this or alkane undergoing treated with Cl2 in the presence of H mu? Free radical substitution.
Substitution.
Okay, substitution. So we have CH3, CH2, CH, CH3, CH2, CH3. Can I say this methyl and this methyl are same, equivalent? Because see, I can substitute the halogen here and halogen here. Both are going to be same. I can also say this CH2 and this CH2 are same. So I can substitute here and here means I don't need to substitute again in the CH2 and CH3. and this CH is different, this CH is different. So I can do the mixture of products now. So what I'll get, chlorination CH2Cl, CH2, CH, CH3, CH2, CH3, one product. Next I can say CH3, CHCl, CH, CH3, CH2, CH3. I can also have substitution at the CH, CH3, CH2, CH3, CCl, CH2, CH3, and I can also have substitution at this methyl leading to CH3, CH2, CH, CH2Cl, CH2, CH3. So how many compounds obtained?
Four.
The total number of isomers. And we have talked about only monochlorinated, monohalogenated only. I have not talked about multi-halogenation, that is polyhalogenation means you can have dihalogenation, trihalogenation, tetra, which will lead to lot of products. Yes or no? In the monohalogenation, how many isomers you got? If I say only structural, you have to go with the only 4, but including stereo we have said. That means where is the chirality developed, we have to check out. In the first compound, is there chiral carbon? Because of substitution of a chlorine at this particular carbon, this carbon has CH2, no chiral, achiral, CH2 achiral. This carbon check out CH, CH3, C2H5, CH2, CH2Cl. It is chiral. Because of substitution at this terminal carbon, you have one chiral carbon developed. And this CH3 achiral, CH2, CH3 achiral, because same hydrogens are there. Next compound, CH3 achiral. This carbon check out hydrogen, chlorine, methyl, and this bulky group. This is chiral. What about this carbon? See hydrogen, methyl,
Chiral.
methyl. This other group chiral.
Chiral.
CH3, CH2, CH3 achiral. CH3, CH2, CH3 achiral. Third compound, CH3 achiral, CH2 achiral. This carbon check out chiral or achiral. This carbon
Achiral.
Chiral.
achiral because we have two ethyl groups. C2H5, C2H5. This is not chiral. CH3, CH2, CH3. There is no chiral carbon in third compound. Fourth compound, CH3, CH2 achiral, CH2, CH3 achiral, CH2 achiral. This carbon also has two ethyls, so achiral. So in third and fourth, you don't have any chiral. So we have a chiral carbon means you can have D and L. So here you can have two isomers. Here you have two chiral carbons, D and L, DD, LL, DL, LD, 4 you will get. Here you have one compound only, here you have one compound only. So for total number of isomers will be 8. Got this or not?
Yes.
These are interesting examples. Whatever I am discussing in the class are very interesting examples. Understand this carefully. If you have any doubts, you are free to ask.
So,
Right? Yes, please.
sir, in the compound that you chose with substitute alkene, sir, to make it
Yes, to make it.
chiral, like chiral, why don't you use chiral, like sir? There you only used carbon compounds, right? So, like attached to the
Yeah, what is A? What is A?
optically active alkene.
Alkene. So the compound A has to be simplest optically active alkene. If I use any other compounds, if I connect to OH group here, is it called as an alkene?
Okay, yes, sir. Yes, sir.
Okay, it has to be alkene ultimately. Whatever the compound you have chosen, it has to be alkene. It cannot be alcohol or alkene. If I have a chlorine, alkyl halide, you will call it. It is not no more an alkene. Okay, that is the reason.
Yes, yes, okay.
So right, students, then comes the E1 elimination. E1 elimination. E1 elimination means you can also call this as unimolecular elimination reaction. Unimolecular elimination. That means the rate of the reaction. The E1 elimination occurs in 2 steps. The E1 reaction occurs in 2 steps. Step 1 is slow ionization to form a carbocation. Step 1 is slow ionization to form a carbocation. And step 2 is attack of base to pick up a proton, and form an alkene. Rate of even elimination. Even elimination means unimolecular elimination reaction. Step 1 is slow ionization to form a carbocation. Step 1, formation of carbocation is the rate determining step. Step 1 is the RDS. And in the rate determining step, we only have substrate. Substrate is undergoing the carbon halogen bond cleavage to form a carbocation. So we only have substrate in the rate determining step. So rate of the reaction is directly proportional to concentration of substrate alone. So step 1 is the RDS, and in the RDS we only have substrate. Therefore, rate of that even elimination is directly proportional to concentration of substrate alone. Rate of even elimination is directly proportional to concentration of the substrate alone. It is not depending upon base. So order is equals to 1. Molecularity is equals to 1. Order is experimentally determined or theoretically determined? Order is experimentally given quantity. Molecularity is theoretically given quantity, and molecularity can never be greater than 3 because it gives idea regarding the number of molecules present in the, like, which are colliding simultaneously. Order is experimentally determined, and whenever you're trying to write the rate law, like if you have concentration of A plus B gives rise to C, rate is directly proportional to concentration of A power X, concentration of B power Y you write, where X and Y has to determine experimentally, but here we are writing theoretically only. We are not determining the experimental quantities because only one reactant is there or only one substrate is there, which is undergoing the carbon halogen bond cleavage. So rate has to depend upon the concentration of that particular species only. That power is taken as 1, applying the law of mass action condition. So order is equals to 1, molecularity is equals to 1, rate depends only upon the concentration of substrate. What do you mean by this? From the rate expression we can also understand, that rate of E1 is independent of concentration of base. So weak bases have to be preferred. Weak bases generally used are water, H2O, and alcohol, ROH. Rate of E1 is independent of concentration of base. So weak bases, generally used weak bases are H2 and water, are used in E1 elimination. If you use a strong base, it preferentially go with the E2 elimination or not, because rate of E2 elimination is directly proportional to concentration of base. So if strong base if we have used, that will preferentially go with the E2 elimination. If we use weak base like water and alcohol, then it will undergo even elimination. But for E1 or E2, you require high temperature. High temperature is required. High temperature is always required. High temperature is required for both E1 and E2. For both E1 and E2. High temperature is required for both E1 and E2 to form as elimination involves cleavage of bonds. As elimination involves bond cleavages. And what is the next point which you can think of? Rate of alkyl halides. Like if I am trying to change the alkyl halide, tertiary, secondary, primary. Tertiary alkyl halide, secondary alkyl halide, primary alkyl halide, which will undergo E1 greatly. Tertiary alkyl halide will undergo E1 greatly, then secondary, then primary. Why? Because tertiary alkyl halide will form a tertiary carbocation. Because the step 1 is the formation of a carbocation. The tertiary carbocation is more stable or not? Because of more number of hyperconjugated structures. Since the tertiary carbocation is more stable when compared to secondary is more stable when compared to primary. So we can say 3 degree carbocation greater than 2 degree than 1 degree. That means CH3, CH, CH3, C, CH3, CH3, Cl. This should be greater. Then CH3, C, CH3, CH, Cl. That should be greater. Then CH3, CH2, Cl. So you can just to summarize SN2. What is the order? SN2 is primary greater than secondary greater than tertiary. SN1 3 degree greater than 2 degree greater than 1 degree. E2 3 degree greater than 2 degree greater than 1 degree. E1 3 degree greater than 2 degree greater than 1 degree. SN1 and E1 you can easily understand because SN1 and E1 we form a carbocation. So tertiary carbocation more stable than secondary than primary. But E2 also 3 degree greater than 2 degree greater than 1 degree. Because in E2 what is the transition state looks like? The transition state looks like alkene. So that is why 3 degree greater than 2 degree greater than 1 degree. And in case of pool leaving group, how the transition state looks like? Carbon ion system. Based on the stability of carbon ion, you have to write the major product. Right? And general reaction we'll consider. So CH3, C, CH3, CH3, Cl plus H2O in the presence of high temperature forms what? Solution goes like this. So first step, alkyl halide. What type of alkyl halide they have given? 3 degree alkyl halide, H2O. Water is a weak base. I am taking water as a base, not as a nucleophile. Why? Because temperature condition is mentioned, so I have to do the elimination only, not the substitution. If I do not mention temperature, what you have to do? If I do not mention temperature, you have to do substitution. Substitution can also occur. At high temperature only elimination will occur. So tertiary alkyl halide, first step 1, first step CH3, C, CH3, C, CH3, CCl undergo loss of carbon chlorine bond. So loss of chloride ion will lead to the formation of CH3, C, CH3, C, CH3 with a positive charge. This is nothing but 3 degree carbocation. 3 degree carbocation. This 3 degree carbocation is now the most stable carbocation or not? 3 degree carbocation is the most stable carbocation. And you have 3 degree alkyl halide treated with water. Water is a weak base. So if it is a strong base, I can think of elimination. E2 elimination. If it is a weak base, that's why I'm going to even elimination. Instead of water, if I give alcoholic OH, you have to do E2. You have to do E2. Since water is given, you have to do E1. Because rate of E2 depends upon concentration of base. Stronger the base, greater the rate of E2. So now we form a 3 degree carbocation, more stable carbocation, no other possibilities of ring expansions or rearrangements because ring is not there first of all, and it is the most stable carbocation. Now water comes into picture. Water acts as a base. So CH3, CH2H I can say, CH2H, C, CH3, CH3, positive charge. Water now acts as a base. Lone pair of electrons on oxygen picks up the proton. The CH electron density comes into. Yes or no? Okay, it is picking up. As soon as the proton is picked up, CH electron density comes into, you will get what? CH2 double bond C, CH3 plus H2O is now going to be converted to H3O with one lone pair and a positive charge, H3O plus. This is nothing but your major product. Same alkene you got, but the mechanistic approach is different. It proceeds through even elimination where you get a more stable carbocation. Is that clear, students?
Yes, sir.
Yes.
Yes.
Try to do some other example. Just a second. One ring expansion you try to do. Yeah, what is the major product? 4-member ring CH2, CH2Cl treated with H2 in the presence of heating. So first, what type of alkyl halide? What type of alkyl halide? Primary alkyl halide. Yes or no? CH2Cl, the carbon connected to halogen is connected only to one other alkyl group. So it's a primary alkyl halide. So there is no tendency to undergo E1 or E2. Both E1 and E2 will have least tendency to undergo. E1 and E2 both have lesser rate for the primary alkyl halides. But you have to decide now. I have to decide whether elimination or substitution. Temperature condition mentioned. So elimination I have to do because elimination involves bond cleavages. So elimination means I have to think of H2 as a base. H2 is a weak base or strong base? Weak base. So weak base means I have to do E1 or E2. E1 I have to do. First step is what? First step is
Formation of carbocation.
formation of carbocation. This type of carbocation is obtained. Or you can just cleave the carbon chlorine bond. Loss of chloride ion will occur to form this type of carbocation. Can I do the ring expansion now directly? Like if I
No,
try
sir,
to break this bond, give numbering 1, 2, 3, 4, 5, 6. I am connecting 6th to first directly. Can I get the 6-member ring?
No, sir.
No, sir.
The
Why? 6-member ring is the
carbon
most stable, right?
carbon
Distance.
difference between
Distance is more, right? So you cannot directly connect any rings as our wish. Distance comes into picture. So you have to do first what?
Hydrate shift.
Hydrate shift 1, 2 hydrate shift you have to do. If I do the 1, 2 hydrate shift, you will be getting this particular carbocation. So now I can do the ring expansion. 1, 2, 3, 4, 5. So 2, 5 bond I can cleave. I can also cleave the 2, 3 bond or not.
Yes, sir.
Because ring expansion is not the rate determining step. You can cleave 2, 5 or 2, 3. Doesn't matter. So first carbon, first is now connected with fifth to fourth, fourth to 3, 3 to 2. First carbon has a methyl substituent. And which carbon should have a positive charge? Second carbon, because it has seen the net loss in electron density. Now we can do the 1, 2 hydrate shift again. 1, 2 hydrate shift you have to do again. So if you do 1, 2 hydrate shift, you will be getting a carbocation like this, which is the most stable carbocation. Now water is there in the reaction mixture. Water will act as a base now. This is the alpha carbon. This is beta. This beta is beta. So the proton from this beta carbon is picked up, and you will be getting this type of alkene. This is a major. Yes or no? Right, students? So these are the different examples of E1 elimination, E2 elimination, electrophilic addition reactions, nucleophilic addition reactions, free radical additions, electrophilic substitution, nucleophilic substitution, free radical substitution, elimination reactions, alpha elimination, E1, E2 eliminations. We do have some other reactions named as isomerization reactions or rearrangements. Those rearrangements we'll discuss whenever, like Fry's rearrangements. Okay, those rearrangements we'll discuss whenever we deal with that particular organic functional groups. Fine. So be prepared well. GOC1 refers to all the electronic effects, like starting from bond cleavages. What type of bond cleavage? Homolytic, heterolytic cleavage. What type of reagents? Electrophiles, nucleophiles. How many classifications of electrophiles are there and nucleophiles are there? After that, what are the intermediates? Carbocation, carbanion, free radical, their stabilities, electronic effects, inductive effect, electromeric effect, mesomeric effect, hyperconjugation. Electromeric effect is temporary, remaining 3 are permanent. With respect to all these 3 effects, we have looked at acidity, basicity comparisons, Brett's rule, tautomerism. Using all those concepts, we have studied about different types of organic reactions. The same organic reactions are going to be repeating many times in different chapters. You can see that. Okay. So this is also called as reaction mechanism 1 and reaction mechanism 2. Reaction mechanism 1 means GOC1. This all whatever I have explained reactions. This is the reaction mechanism 2 part. You don't confuse with that names. Okay. So let us start with a new chapter. As I have told you yesterday, which chapter we are going to start today?
Purification.
Purification. Very good. So purification is important or not? Let us say Fatima done one reaction. She got a mixture of products. She have to separate whatever the A, B, C products she got. A is a major product, and if she want only A means she has to separate the A from the mixture B and C. Like A, B, C from the mixture of A, B, and C, I have to separate out A. How is that going to happen? How is that going to happen? There are different techniques. Okay, all those techniques we'll study now, students. So anyone remember the techniques, how you can actually separate A and B? It depends upon either boiling points, either solubilities, yes or no. Lot of properties are there. Based on the properties of A and B only we can comment that whether the separation is going to happen or not. After the separation is done, what you have to do? Like if I am asking to prepare one compound, you will do some reaction, organic reaction. From the organic reaction, you got a mixture. Using your knowledge by studying the properties of all the compounds A, B, and C, we have separated out A. Now you again show me, sir, this is the compound A which was the pure compound. Then again I'll say I won't believe that whether the compound A is true or not. So what is the proof that you have prepared the same compound? That means you have to support it by some characterization techniques. I will be giving some data which refers, yes, in this particular A molecule, this is a molecular mass based on molecular spectroscopy or mass spectroscopy. This is the NMR, nuclear magnetic resonance. Based on NMR, these are the positions of different groups. These are the IR, infrared ray spectroscopy, where the different bonds have different types of vibrational frequencies. I'll be providing the supporting data which says, yes, the molecule, whatever I have given, and whatever the molecule I have prepared, both are same. Then only we can do some research, we can do the reaction, we can study about rates of reaction and all. That is how you will be studying in the future as well. Like biochemistry, you all study once you become doctors. Yes or no? It is obviously important subject. Microbiology, biochemistry, chemistry plays an important role. So that is how organic chemistry will be affected. So purification is a very important part to actually prepare one organic compound, to actually study an organic compound. Like I have done a reaction, that's the first stage. Purify, get a pure compound, second stage. Confirm whether the same compound you have prepared or not by doing the characterization, third stage. After getting, yes, this is my right compound, do its research. Like I am going to do that, use that compound in different types of reactions. Understanding how it is behaving. That is the fourth stage of the application stage. Yes or no? We have to prepare a drug or medicine means we have to do in the same manner. So the pure until now, whatever we have seen, the reactions, we have just studied what is a major product. Whatever the reaction, electrophilic substitution, E1, E2, SN1, SN2, SNI, different mechanistic approaches. What we have explained, how to write the major product using some techniques. But you always end up with a mixture of products. So these methods of purifications are very important to separate the mixture of products into pure. So organic compounds are obtained either from natural source or synthesized in laboratory or contaminated with impurities always. Various methods are used for removal of impurities from an organic compound, and that depends upon nature of compound and the type of impurities present in it. Various methods are used for removal of impurities from organic compounds, depends on the nature of compound and type of impurities present in it. So most of the pure compounds contain sharp melting and boiling points. So based on the type of impurities and the properties, we have different techniques of purification. Anyone remember what type of techniques we have? We only have broadly 5 techniques: sublimation, crystallization, distillation, solvent extraction, chromatography. In the chromatography also, we have only adsorption chromatography and partition chromatography, like column chromatography, thin layer chromatography or TLC, and paper chromatography. We don't have gas chromatography. Gas chromatography will be in the higher stage. In the distillation, we have 4 types: simple distillation, fractional distillation, distillation at a reduced pressure, steam distillation. Yes or no? So let us understand these techniques, students. Methods of purification. As I have told you, we have sublimation, crystallization, distillation, solvent extraction or differential extraction, and chromatography. So start with one by one. Sublimation means what? Simple technique, we have a compound, like mixture of compounds A, B, and C are there. Let us say B and C are impurities. A is pure. And the pure compound A has to be sublimable, whereas the impurities are non-sublimable. A, B, and C are there. If A is sublimable, I can simply give the heat. I'll provide the heat in such a way, such that how I can convert the compound A directly into the gas phase without going into liquid? How I can do that?
Sublimation. Sublimation.
Sublimate.
Yeah, I have to provide heat such that the temperature is not going to be reaching the melting point. If the temperature reaches the melting point, obviously the solid is going to be converting into liquid. That we have to erase. So A is directly converted to gas. So sublimation is new methods of checking the purity of compound are based on different types of chromatography and spectroscopy techniques. As I have told you, gas chromatography. There are other methods as well, AFM, XRDs. You will study about those in the future, in the higher levels. The process of conversion of sublimable solid to vapor state directly by heating without passing through liquid state is called sublimation. A is a pure compound, A is directly converted to gas. A pure solid is converted to gas. Yes or no? In this technique, what you can say? This method is used for the purification of solids. So from the mixture of compounds, one of the compounds should be solid. The organic compound, whatever pure compound you are assuming, that has to be solid. Sublimation process is used for separation of sublimable volatile compounds from non-sublimable impurities. If impurities are also sublimable, then what's the point? If I give heat, all of them will go into the vapor state. They are earlier all of them are in the solid state. Now I have given heat, all of them went into the vapor state. So there is again a mixture. No separation happened. So the pure compound or whatever the required compound that has to be sublimable. The remaining are non-sublimable impurities. Sublimation is generally used for the purification of camphor. These examples, wherever we are giving, you write down or you understand it. I'll be sharing it in the handouts. Ultimately, you have to remember the examples. That is very important for every case. Sublimation is generally used for the purification of camphor, naphthalene, anthracene, benzoic acid, phthalic anhydride, anthraquinone, indigo, and iodine SO3, solid SO3. Is that clear, students?
Yes.
Is that clear to everyone or not? All of you should respond.
Yes. Yes, sir.
Yes, sir.
Yes. So this is what your sublimation techniques, which is very, very simple technique. Crystallization, based on which you can understand crystallization or what are the technique involving crystallization. Crystallization, most commonly used technique for purification of organic compounds. This is nothing but crystallization. These are mostly used. Crystallization is based on the difference in solubilities of compound and impurities in a suitable solvent. Simple logic is, we have taken a particular solvent. In that particular solvent, you are adding the pure compound. That means not adding, you are doing a reaction where you have pure compound and impurities both are present. Pure and impurities both are present. Understand this point carefully. The principle involved in this method is impure compound dissolved in a solvent is sparingly soluble at low temperature, but appreciably soluble at high temperature. This is the principle. Impure compound, whatever you are taking, that is sparingly soluble at a low temperature. Sparingly soluble means what is the solubility? We have studied ionic equilibrium. For sparingly soluble salts, solubility should be less than 0.01 molar. If you remember ionic equilibrium solubility, if it is less than 0.01 molar, we call it as a sparingly soluble. So whatever the impure compound you have, that is sparingly soluble in the solvent, sparingly soluble in solvent at low temperature. But if you increase temperature, what happens? The dissociation increases, so solubility should increase. So, but appreciably soluble at high temperature. Insoluble impurities, whatever they are there, they are separated by filtration. Like you have a funnel. I have a particular beaker, let us say. In this beaker, I have pure solid as well as impurities. I am just heating this. Why I am heating this? So whatever the insoluble impurities are there, the insoluble impurities, even though I give heat, they are not soluble. Whatever the soluble pure compound is there, that pure compound is soluble at high temperature only, not low temperature. So initially I have some rocks, let us say impurities are rocks, and we have pure compound, which is also present in the solid form because not soluble at low temperature. I have given heat. Since I have given heat, what happened? What happened is all the whatever the heat I have given, because of that heat, the pure compound which was in the solid state that went into the liquid state because it is soluble. Now what do we have? At higher temperature I have only rocks and the pure compound is in the liquid state. Now what I am going to do is I am using a filter paper, separate out all the insoluble rocks, and I have a mixture of solution where you have pure compound. What I am going to do later? I am going to reduce the temperature. If I reduce the temperature, again solubility has to decrease or not? Yes or no? So that means whatever the pure compound which was in the liquid state, that will come out on cooling. On cooling the saturated solution, all the pure compound which was in the liquid state, that will come out as the crystals. Crystallization occurs. Understood this point or not?
Yes, sir.
Yes.
Okay. If a compound is highly soluble in one solvent and too little soluble in other solvent, then crystallization is carried out using mixture of these solvents. Impurities which impart color are removed by adsorbing over charcoal, because if you add charcoal, whatever the impurities which are imparting color, they will get adsorbed. Repeated crystallization is required if organic compound contains impurities of compatible solubilities. So what I am saying is impurities, some rocks, and we have pure compound in solid state. This I am giving heat. Because of it, what happened? Pure compound in liquid plus impurities or rocks. Now I am doing the filtration. I'll have pure compound in liquid. Then I'll do cooling. Cooling the saturated solution. Cooling the saturated solution, I'll get pure compound crystallizing out. So whatever the logics we are saying here, repeated crystallization is required if organic compound contains impurities of comparable solubilities. Yes, if the impurities are rocks, then I can do easily remove by filtration. But if they are also slightly soluble, comparable solubilities are there, then you have to do the crystallization many number of times so that we get the pure compound. And impurities, if they impart color, we have to add activated charcoal so that all the colored impurities, they will be getting adsorbed. Okay, this is the technique of crystallization. Everyone got clear with this or not?
Yes.
Yes,
Yes.
sir.
That's right. So then comes the distillation. Next technique. Distillation means what? Distillation you have to use when there's a difference in the boiling points. Distillation is actually classified into 4 types: simple distillation, fractional distillation, distillation under reduced pressure, and steam distillation. Distillation is an important method used to separate volatile liquids from non-volatile impurities. Liquids having sufficient difference in boiling point. These are the conditions. Volatile liquids from non-volatile impurities. If the impurity is non-volatile and we have volatile liquid, that volatile liquid from non-volatile impurities can be separated. And liquids having sufficient difference in the boiling points, the liquid should have sufficient difference in the boiling points. I have just said sufficient difference, but what is that sufficient? We have to classify. So classification of not colloids, distillation. We have simple distillation. We have fractional distillation, distillation at reduced pressure vacuum distillation, and steam distillation. In the simple distillation, to perform simple distillation, the 2 compounds should be having a difference of boiling point greater than 40 degree. If the difference in boiling point is less than 40 degree, then you have to do fractional distillation. Simple distillation is very simple. Yes, it is simple only. So this process is used for the purification of liquids which does not undergo decomposition at boiling points. Very, very important point. If I am having a liquid A is a liquid which can go into A into vapor stage at 100 degrees Celsius, let us say. At 100 degrees Celsius, if A is converting into B, another vapor, then am I using this technique? if at 100 degrees Celsius, if at the boiling point or near to boiling point, if A is converting into some other compound, if A itself is converting into some other compound, then how can we supposed to call this as a purification? Yes or no? Because we are not getting A at all. So we are not going to use simple distillation if a compound is going to decompose at or near to, at or below the boiling point. Same fractional distillation also we should not use whenever the decomposition happens near the boiling point. Technique is the vaporization of liquid by heating and subsequent condensation of vapors by cooling is called distillation. That means you have a mixture A and B. You are heating it. Let us say A has less boiling point. So what vapor you will collect first? Vapor of, if A has lesser boiling point, it will be going into the vapor state first or not? If A has lesser boiling point, A will be going to the vapor state first. So vapor of A will connect, and then you can condense it back. Condense it to get pure A in the liquid state. So it is used for the liquids, and if we have a mixture of A and B, that mixture of A and B can be converted to the vapor state. That vapor, first you can get the vapor of that component which is having lesser boiling point. So lesser boiling point vapor will be condensed back, so you will get the distillation. You can perform the distillation so that you can separate A and B. The vapors of liquid by heating and subsequent condensation of vapors by cooling is called distillation. Liquid mixture is generally taken in a round bottom flask and heated carefully. The round bottom flask can be heated carefully. The component with lower boiling point distills first. That's what we have said. Component with lower boiling point will go into vapor phase first and it will condense back. The vapor formed is condensed by using condenser and the liquid is collected in a receiver. The vapors of a component with higher boiling point distills later. If a component has high boiling point, it will be going into the vapor state later stage only. So that will distill later. Is that clear, students? Simple distillation.
Yes, sir.
Very simple. All these techniques you can understand. As I have told you, the boiling point difference has to be greater than 40. The liquids that have boiling point difference greater than 40 degrees can be purified in this method. If the boiling point difference is greater than 40 degrees only, then you can apply this particular method and do the purification. If not, you have to go with the fractional distillation. Examples is chloroform and aniline, ether and toluene, benzene and aniline. So they can actually be separated or purified using this particular separation technique known as simple distillation. Right? So these examples you don't need to write down, just understand, but you have to remember ultimately from the handouts, whatever I have shared, you have to remember this. Because they will ask me questions. So chloroform and aniline can be separated, can be purified by using which separation techniques? A, sublimation, B, crystallization, steam distillation, and chromatography. You have to pick the right one. So this is what the animation looks like. All of you just do the animation. Okay, we are heating it first. So whenever we are heating it, the liquid is going to be converting into vapor. First you will be getting one vapor. Whatever the vapor we have, that has been passed to the condenser, and again you are getting the same liquid in the pure state. Like from the mixture you are getting a pure liquid or not. So like that you will be doing it for longer time where the separation of the two liquids has been done, that is two components has been done. Fractional distillation is very interesting. This is the same technique which we use in the crude oil also. Crude oil also has different fractions. We use fractional distillation only. Fractional distillation is used if the difference in boiling point of two liquids is less than 40 degrees. And here also the compound should not be going into or decomposing near or greater than the boiling point. Vapors of liquid mixture are passed through fractionating column before condensation, which is fitted over mouth of round bottom flask. vapors of liquid with higher boiling point condense before the vapors of liquid with lower boiling point. How this can happen? Third point. Vapors of liquid with higher boiling point condense before the vapors of liquid with lower boiling point. How is that possible? Earlier we have understood, right? In the simple distillation, whatever the component which we have with the lower boiling point, that will be going to the vapor state. That vapor you separate out correctly and condense it back, you get the liquid. But how can you collect the vapors of liquid with high boiling point? They are going to be condensing before the vapors of liquid with low boiling point. To that, let us understand the crude oil separation and all. Okay. FD, fractional distillation. Fractional distillation is even used to separate crude oil into different fractions. Crude oil into different fractions. So what we are going to have here, fractional distillation is even used to separate crude oil in different fractions. So we have a fractionating column that will be something like this. So we have in the crude oil, what is crude oil, students? Anyone know about crude oil? Crude oil contains a mixture of hydrocarbons. It is the greatest asset one can possess as of now. Crude oil has actually containing mixture of hydrocarbons, organic molecules only, everything. If you heat the hydrocarbon, if you get energy, that is sufficient to produce a lot of asset. Yes or no? Mixture of hydrocarbons will be containing in crude oil. Hydrocarbons, let us take simple hydrocarbon like CH3, CH3, and a very high hydrocarbon like CH3, CH2, 8, CH3. Which will have higher boiling point among these two? High boiling point. Like I have ethane and decane.
Again,
Decane.
Because boiling point is directly proportional to molecular weight.
molecular mass.
Molecular mass. Very good. Now I have this crude oil at the lower part of the fractionating column. So this crude oil is present in the lower part of the fractionating column, and we have different layers passed like this. Theoretical plates were kept in this fashion to pass the vapors. Some 100 to 200 plates were placed in this manner. What we are going to do is, whatever the crude oil we collected or we dig from the ocean or from the ground, that is what ONGC people will do. So they will collect the crude oil and they will place the crude oil in the lower part of the fractionating column. At the lower part, the temperature is very high. Temperature is high. If temperature is very high, and in the top part temperature is low. If temperature is very high in the lower section, can I say in the crude oil, even though we have simple hydrocarbon or very high molar mass hydrocarbon, all of them are going into the vapor state or not? Because temperature is very high in the lower part. So temperature with higher means low molecular weight hydrocarbon as well as high molecular weight hydrocarbon, they are going to be going into the vapor stage. But as you go from bottom to top, temperature is decreasing. So that means whatever the high molecular weight hydrocarbon we have, that cannot reach the top. Why? Because the high molecular weight hydrocarbon has higher boiling point. As it goes to some part of the region, it will not, the temperature is not sufficient high to have that molecule in the vapor stage. So it will again come back to the lower stage. Understand this point? We have this bottle again, imagine as a fractionating column. Bottom temperature is very high. We have many plates, fractionating plates. Temperature very high, so crude oil have poured. So all the hydrocarbons go into vapor phase. So they are going into vapors. low hydrocarbon, low molecular mass hydrocarbon, that will reach the top because it will have lesser molecular weight, lesser boiling point. So temperature, low temperature also it can stay in the vapor phase. But high molecular weight hydrocarbon, that can reach from the bottom to some part. That depends upon molecular mass up to what range it went. After reaching some extent, temperature is decreased. So at low temperature, that high molecular weight hydrocarbon cannot stay in the vapor. So it will come back down. So which is condensing back first? High molecular weight hydrocarbon or low molecular weight hydrocarbon?
High
High
molecular.
molecular.
High molecular weight hydrocarbon because it has higher boiling point. So which compound is condensing back first? Vapors of liquid with higher boiling point condense first because they are in the fractionating column. It is not like a simple distillation. Understood this point or not, all of you?
Yes, sir.
Okay, vapors of liquid with higher boiling point, they are condensing before the vapors of liquid with lower boiling point, because as they are moving, as the vapors are rising up, the temperature is decreasing. As the temperature is decreasing, the high molecular mass vapor or high molecular mass hydrocarbon with higher boiling point cannot reach the top, rather it comes down immediately. So condensation is happening for the liquid with higher boiling point first, not for the liquid with lower boiling point. The lower boiling point liquids, they reach the top and they will be condensed back separately. So vapors of liquid with higher boiling point condense before the vapors of liquid with lower boiling point. The vapors rising in the fractionating column, this is nothing but a fractionating column, is richer in more volatile compound. Obviously, whatever the vapors which are rising, they are more volatile or not. So if they are not volatile, if we have low, we will be having lower boiling point compounds in the top region. So vapors rising up in the fractionating column is richer in more volatile compound. Each successive condensation and vaporization unit in the fractionating column is called theoretical plate. These are nothing but your theoretical plates. What are plates? These are nothing but your theoretical plate or fractionating plate. Each successive condensation and vaporization unit in the fractionating column is called theoretical plate. Liquids forming a constant boiling mixture. Anyone known about azeotropic mixture? We have studied in solutions. Okay. So liquids forming a constant boiling mixtures or azeotropic mixtures cannot be used by separated by this method. Azeotropic mixture means mole fraction of the component in the vapor phase is equal to mole fraction of the component in the liquid phase. XA is equal to YA. In that case, you can say azeotropic mixture. Constant boiling mixtures. We'll study about azeotropic mixtures more and more details in solutions chapter. Fractional distillation is used to separate different fractions of crude oil in petroleum industry. That's what I have explained here. This method is used for separation of mixture of acetone 330 Kelvin and methyl alcohol 338 Kelvin. Acetone and methyl alcohol, you can just look at the difference in boiling point, just 8 degrees. That low boiling point difference can be sufficient. That is less than 40 degrees means you have to use fractional distillation, not the simple distillation. Is the concept clear, students?
Yes, sir.
Yes, sir.
Right. You can just look at the animation again. So water and ethyl alcohol, you are heating it. So we have fractionating column, we have plates kept there. You can easily see that. So vapor, whatever it is going up. So some are falling down. You can see. Yes or no? Which are falling down? Which are falling down?
Water.
Water.
Yes or no?
Yes.
So the higher boiling point compounds will be falling down. And low boiling point, whatever we have, they will reach the top and they can be condensed back. They can be condensed back. Right. Next technique, distillation under reduced pressure, vacuum distillation. This is used whenever a particular compound is undergoing decomposition at the boiling point or near to its boiling point. How the boiling point is going to be proportional to atmospheric pressure? Boiling point is directly proportional to atmospheric pressure. And what about vapor pressure? Boiling point is inversely proportional to
Vapor.
vapor pressure. Yes or no? Boiling point is directly proportional to atmospheric pressure, whereas inversely proportional to vapor pressure. So if a particular liquid has a boiling point of 100 degrees Celsius, let us say, but at 100 degrees Celsius, it is converting into another compound B. A compound A is there. It has a boiling point of 100 degrees Celsius, but at 100 degrees Celsius, it is converting into B. So what I can say in that case? In that case, what I can say? If a particular liquid A is converting into B at 100 degrees Celsius, what I can say, students? That means I am not supposed to use the steam distillation or fractional distillation, because at the boiling point, it is converting into other compound. Decomposition is happening. So I have to reduce the boiling point of that particular component. How I can do that? I can reduce the pressure or not? Atmospheric pressure. So this method is used to purify liquids having very high boiling points, which decompose at or below their boiling points. So these liquids are made to boil at a temperature lower than their normal boiling point by reducing the pressure on the surface. So I have particular liquid. So boiling point is the temperature at which vapor pressure is equals to 1 atmosphere, atmospheric pressure. So whatever the liquid we have, above that liquid, whatever the vapor we have, I am trying to remove all that vapor with the help of vacuum pump. I'll insert a vacuum pump, suck out all the vapor, whatever I have. Yes or no? If I remove the vapor, what is going to happen, students? If I remove the vapor, what is going to happen?
Concentration
The
will
pressure is decreased. If the pressure is decreased, if the atmospheric pressure, if that pressure is decreased above the surface, the pressure is decreased. Obviously, the boiling point decreases. So boiling point is decreased. That means the liquid is now going to undergo boiling at a lower temperature than its original boiling point. So glycerol can be separated by spent lye in soap industry by using vacuum distillation. So this example is very, very important. Glycerol can be separated by spent lye, separated from spent lye in soap industry in the usage of vacuum distillation. Like by using vacuum distillation only or distillation at reduced pressure only, we are going to do this. So complex technique will be there. So this is the apparatus and all. These operators, diagrams and all not required, but just you have to understand we have to reduce the pressure above the surface of liquid. So under reduced pressure, the boiling of that liquid happens at a lower temperature than its original boiling point. At that original than the original boiling point, boiling is happening. So such that you can actually do that distillation. Okay, you have placed the vacuum pump. Vacuum pump removes all the particular pressure. So boiling is now going to happen at a lower temperature than the temperature at which the liquid has to boil because of the placement of boiling vacuum pump. So then you have steam distillation. Steam distillation means what? Steam distillation means the method is used for separation and purification of organic compounds which are steam volatile and are insoluble in water. In the steam, the organic compound should be volatile. And whenever I decrease the temperature, steam will be decreased to what? If I decrease the temperature, steam will be condensed to H2O. Organic compound which is in the solid state, it will convert to organic compound in liquid. The organic compound should be volatile in steam and it should not be soluble in water. If it is soluble in water, again we have a mixture of water and organic compound. The separation becomes difficult. So like I have impurities, organic compound in the solid state and steam is there. Steam volatile organic compound, whatever it is there, that is actually the steam is passed to the mixture of organic compounds. The organic compound pure one will be volatile in the steam. That means it will come into the vapor state. Once it comes to the vapor state, you can collect all that vapor. What is the vapor? Vapor of steam and organic compound. That you can condense back. If steam is condensed back, you get water. If organic compound in the liquid state is condensed back, you get organic compound in the gaseous state, if that is condensed back, you will get liquid. If the organic compound of liquid is soluble in water, then again this method is not used. So the solids or liquids which are steam volatile and are insoluble in water, those were actually used in this steam distillation. In the steam distillation, steam from steam generator is passed through a heated flask containing the liquid to be distilled. The mixture of steam and a volatile organic compound is condensed and collected. The compound is later separated from the water using a separating funnel. What do you mean by that? In the water, that organic liquid is insoluble, means water and organic liquid separates into two distinct layers. So you have a separating funnel. You can see separating funnels will be somewhat like this. Okay, the diagram may not be exactly clear. You can have some separating funnels in this fashion. Stopcock will have at the bottom. So we have one layer separating out, other layer separating out. Yes or no? From the top, you will be having the like water and that particular organic compound in liquid stage. Like water and kerosene you add and keep it separate. The oil or the kerosene that will separate out into distinct layer. Water separates in distinct layer. Once the distinct layers are separated out, you can usually separate one layer from the other layer because we can actually detect it. Clear or not, students?
Yes, sir.
Yes.
Okay, so these are your different techniques. So next class we'll proceed with the next other techniques, and after this we'll study about qualitative analysis and quantitative analysis, then proceed with hydrocarbons. Fine, thank you all. Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.